Okay, hello everyone. So welcome to this live session for week 4 of this course, Introduction to Galois Theory. So this is instructed by Professor Krishna Hanumanthu. Uh, so as usual, before solving some problems, I will summarize the main contents of week 4. So, so let's list down the key topics of this week. So in this week, we started with various characterizations of Galois extensions, or particularly finite Galois extensions. So let's write down those things. So characterizations of Galois extensions. So particularly if K over F is a finite field extension. So K over F is a finite extension of fields. Then the following are equivalent. So we have all these equivalent conditions. Uh, so the first thing is that numerical characterization of Galois extensions. That is basically the degree of this extension is same as the cardinality of the Galois group. So this is the first one which we have seen in the previous week. And next is the that the so if you take the fixed field of the Galois group, then this is same as the base field. So this we have considered as our definition of Galois extension. So these two things which we have already seen in the previous week, and in this week we have seen that K is the splitting field. K is the splitting field of a separable polynomial. Of a separable polynomial, let's say, okay, let's not mention it. Of a separable polynomial over f. So this is the third condition. We started this week with the proof of this statement, and the fourth one is just a consequence of this one, which is K is both normal and separable extensions of F. Okay, so K over F. So K over F is both normal as well as separable. So we have these four equivalent conditions for an extension to be Galois. So so K over F satisfying any so K over F satisfying any one of the above equivalent conditions is called a Galois extension. So these are the characterizations, and we have seen some consequences of this result also. Like any finite separable extension can be extended to a Galois extension, and using that we can define Galois closure. So first, let me write down this. So any finite separable extension can be further extended to a Galois extension. And smallest such Galois extension is called the Galois closure. So I will come to that when I will do some problems. But let me finish first the summary of this topic. And after that, we have seen when a finite extension of a perfect field is Galois. So a finite extension of a perfect field is Galois if and only if it is normal. Because as we know that finite extension of perfect fields are always separable. So uh, to get the Galoisness, we just only need the normality condition. And after that, we have seen several examples to motivate the fundamental theorem or the main theorem of Galois theory. So examples to motivate the fundamental theorem of Galois theory. Then we have also done the fundamental theorem of Galois theory, in which we have particularly done two statements. So in which the first statement is about the so if we have a Galois extension K over F, so the first statement relates the intermediate fields and the subgroups of the Galois group. So there is a inclusion reversing one correspondence between those two, and the second one is when intermediate field is Galois, about that one. And after this we have seen one or two consequences of this fundamental theorem. So one of this is a finite separable extension. So if you have a separable extension and it is also finite, then it can have only finitely many intermediate fields. So finite separable extension has only uh, finitely many intermediate fields. And using this, one can prove one sufficient case of the primitive element theorem. But I think it is there in the last week, so we can wait till the last week. And in the end, we have done one proof of fundamental theorem of algebra using the Galois theory. So proof of the fundamental theorem of algebra using Galois theory. So there are various proofs of this result is available, but we have done this using the Galois theory. So these are the topics of this week. Now let's come to some problems uh, so that we can grasp the contents of this week, and also we can solve the assignment problems. Okay, so let's do the first one. So let's start with the Galois extension. So let E over F be a Galois extension, or finite Galois extension. So let's be more specific. And suppose the Galois group of E over F is isomorphic to Z mod 20Z product with Z mod 2Z. So we are given a Galois extension, and whose Galois group is particularly given that it is isomorphic with Z mod 20Z cross Z mod 2Z. Now determine the number of intermediate fields intermediate field L uh, of this extension E over F such that the following conditions hold. Such that the first one is this degree of L over F is 4. So this is the first one. Second one is degree of L over F is 25. And third one is uh, this Galois group of E over L is isomorphic with Z mod 5Z. So intermediate field means we have this extension E and we have F here. So L will lie between E and F. So that's why L is an intermediate field. So we need to find the number of these subfields satisfying each three conditions. So the problem is very simple. So let's do it one by one. So let's do the first one. So note that as we have E here and L here, and in the below we have F. So this one is 4 and this whole extension, okay, let me write down. So since E over F is Galois, so the degree of the extension must be same as the cardinality of the Galois group. So this is from the characterization of Galois extensions, and this is same as cardinality of Z mod 20Z cross Z mod 2Z, and from group theory we know it is 40. So this cardinality of this, sorry, degree of this extension is 40, and we know that degree of extension is multiplicative, right? So this one is 40 and this one is 4, so this one has to be 10. Thus so let me write down specifically. So we know that this degree is basically degree of E over L times degree of L over F, and this is basically 40 equals to degree of E over L times 4. So degree of this extension E over L has to be 10. So we need to find the number of intermediate fields L such that this degree E over L has to be 10, right? And this extension is Galois. So now we can use the fundamental theorem. So this intermediate field L uh, is in one correspondence with a subgroup of the Galois group of E over F. So we need to use that. So this degree is 10, and this is also Galois, right? So this will imply, so since E over L is also Galois, so cardinality of the Galois group E over L is also 10, right? So this is from the characterization of Galois extension. Now we need to find this number of such intermediate fields. So now by the fundamental theorem of Galois theory, such intermediate fields L with this degree is 10 is in 1-1 correspondence uh, with the subgroups of the Galois group. Okay, let me write just subgroups of the group Galois of E over F. Okay, I should put a name for this, otherwise. So subgroup H of the Galois group is such that cardinality of H is 10, right? Then the fixed field of this H will be the field L. So here we have this collection of intermediate fields of E over F. So here we have this collection. Then we have one-on correspondence with subgroups of the Galois group. And how this correspondence is defined? we have take a field L here and we just send it to the Galois group of E over L. And the reverse map is basically we take a subgroup H and we just send it to the fixed field of this subgroup. So this is the first statement of the fundamental theorem of Galois theory. We have done this. We just have to use this statement. So now the problem reduces to the group theory problem. So we need to find the number of subgroups of the group, let's say G, which is the Galois group Z mod 20Z cross Z mod 2Z of order 10. So that will give us the answer. Now this is a purely group theoretical problem. This is also easy to do, but let's do this. So we have to find the number of subgroups of order 10. Now, in general, there are only two subgroups. Two groups of order 10. Right. Now, uh, a group of order 10 is either isomorphic to Z mod 10Z, means either it is a cyclic group of order 10, or if it is non-abelian, or it is isomorphic to D5, the dihedral group of order 10. So dihedral group of order 10. So I mean, up to isomorphism, there are only two groups of order 10. So one is the cyclic group of order 10 and other one is the non-abelian group, which is D5. But in our case, this subgroup H of order 10 is a subgroup of G, and G is abelian. So every subgroup of G is also abelian. So it has to be Z mod 10Z. It has to be cyclic group. So if H is a subgroup of G of order 10, then H must be isomorphic to Z mod 10Z, right? Because H has to be abelian. So we need to basically find the number of cyclic subgroups of order 10, and it is basically same as finding the number of elements of order 10. So thus we need to find the number of elements of order 10 in this group Z mod 20Z cross Z mod 2Z. And it is as usual way, we have already done this thing. So let's do this one more time. So let A comma B belongs to, so this is our group G. So belongs to G, be an element of order 10. So we have to find all the possibilities of this element. Be an element of order 10, right? Then we already know this order of this element A comma B is same as order of LCM of order of A comma order of B. But this is 10. So what are the possibilities? So there the possibilities are order of A is 10 and order of B is 1, so that the LCM becomes 10. Or, okay, let me write thus. So this is one possibility. The other one is order of A is 10, order of B is 2, and the other possibility is order of A is 5 and order of B is 2. So you can check that we have only these three possibilities, in which case we will get the order of this A comma B is 10. So there will be no other possibility. Yeah, so there will be no other possibility, and in each of these case we have to find the total number of elements. So in the first case, so order A is in Z mod 20Z and order of A is 10. So there will be only 4 elements that you can check. So in this case, okay, so I will write down in the side of this. So in this case we will get 4 elements. In this case also we will get yeah, in all these three cases we will get 4 elements. So in total we will get 12 elements. So now from this, so the number of subgroups of order 10 is basically you just take the number of elements and divide it by the, so what we are finding the number of subgroups H whose order is 10 and H is cyclic. So in a cyclic group, how many order 10 elements can be there? So it is basically the phi of 10, right? So this is Euler phi function. So we have total 12 elements and 12 elements of order 10, and in a subgroup of order 10 there is only 4 elements. So this is 12 by 4, so 3. So there will be 3 subgroups of order 10, and this will imply that there are 3 intermediate fields, L, such that the degree of L over F is 4. So this will give you the final answer for the first one. So for this, the answer is 3. Okay, now let's do the second one. So we have to find the number of intermediate fields L such that degree of L over A is 25. So this case is fairly easy. So if L is an intermediate field, so intermediate field of E over F, so that means we have E in the top, L in the middle and F in the bottom, such that degree of this L over F is 25. So this degree is 25 and this degree is 40 that we have already got, but degree is multiplicative, right? But 25 does not divide 40, but we know that degree of L over F must divides degree of E over F. That is so that's a contradiction. So this will imply that 25 divides 40, but this is a contradiction. So this implies there is no such intermediate field. So the second one is fairly easier.
Sir, one doubt.
Yes.
In the first one, we divided the 12 by the Euler function of 10.
Yes.
How we are getting the exact number of subgroups from by dividing by Euler function of 10 actually?
So
Because this all 12 has order 10. So we can generate order 10 subgroup with all of these 12.
yeah, basically what we are doing, we are finding the total number of subgroups of order 10, right?
Yes, sir.
And all such subgroups are cyclic groups. And in a cyclic
Yes.
group of order 10, there are exactly 4 elements of order 10. So we have
Oh,
found the uh, elements of order 10, all elements of order 10. So there are total 12 such elements. And
yes, sir.
in particular, one subgroup, there can be there can be exactly 4 elements.
Yes.
So we are just dividing by that number.
Okay, sir. Okay, okay. Sir, but what if two of these elements are having the same subgroup?
No, in a subgroup, the generators has to be distinct, right? So in
Yes, 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 sir.
yeah, so this degree order 10 elements are the generators, and there can be
Oh,
exactly 4 generators.
okay, sir. Thank you, sir.
Yeah. Okay, so we have done the first two. Now let's do the third one. So in the third one, we need to find the intermediate field L such that the corresponding Galois group is isomorphic to Z mod 5Z. So C. So let L be an intermediate field of E over F such that the Galois group of E over L is Z mod 5Z. So we need to find the number of such intermediate fields. So by the fundamental theorem, basically we need to find the total number of subgroups of order 5, exactly as we have done in the first case. So by the fundamental theorem, we have to find the number of subgroups of the Galois group of the bigger tower, subgroups of G of order 5. So again it is similar to the finding the number of elements of order 5. So let A comma B belongs to G be an element of order 5. So again 5 is same as the order of this pair A comma B, and from group theory we know that it is same as LCM of order of A comma order of B. Now let's write down the possibilities one by one.
There is exactly one possibility.
Uh, is it so? Okay, let me check and let me write down. So here order of A can be 5 and order of B can be 1. So LCM of 5 can be done in just two ways. One is 5 and one is 1, and the other one is 1 and it is 5. And
Sir, but B is coming from
yeah.
Z2.
So I am just listing down all the possibilities, then I will discard one by one.
Oh, okay.
Yeah. So, and this is the order of both are 5. But B is coming from Z2, so its order cannot be 5. So we have only one possibility. So you are correct. So this is 0 elements. Here also 0 elements. But in the first case, we need to find number of elements in Z mod 20Z of order 5. So it is easy because it is a cyclic group. So number of elements of order 5 is phi of the Euler phi function.
Fine.
So it is 4. So total we have 4 elements. And in a cyclic group of order 5, there can be 4 elements and we have just 4. So there can be there is exactly one such subgroup. So the number of subgroups of order 5 is basically the total number of elements of order 5 by the phi of 5. So this is 4 and this is also 4, so this is 1. So in this case we have only one intermediate. So this is just merely an easy application of the fundamental theorem and some group theory. So I hope it is understandable.
Yes, sir.
Uh, let's do little bit complicated ones. So this is problem number 2. Okay. So give an example. Example of a tower of fields. Tower of fields like so Q, the field of rational numbers, sitting inside F1, sitting inside F2, which is sitting inside F3, uh, such that these three conditions hold. The first one is degree of the bigger field is 8, and second one is each field in this tower in the tower is Galois over all its subfields except F2 over Q. Okay, so let me explain the second condition. So basically we have to find a tower like this, F2 sitting over F1, which is sitting, sorry, F3 which is sitting over F2, which is sitting over F1, and the base field is Q. So we are in characteristic 0, such that the degree of this bigger one is 8, and if we take this extension f3 over q, or f1 over q, or f3 over f2, and even f2 over f1, so all these extensions are Galois. Just one extension is not Galois, just f2 over q is not Galois, and all other extensions are Galois. Yeah, did you understand the problem?
Yes, sir.
Yeah, okay. So we have to find such tower with these two properties. So how to construct such extension? So the main fact is this second part, that this f2 over q is not Galois. So let me write here that this one is not Galois. So how to construct such extension? So first let's do one easy observation, that this degree is 8. So degree of this intermediate one has to be 2. So since degree of f3 over q is 8, so this will imply degree of f3, how to write it? Okay, so f3 over f2 is 2, and this is also same as degree over f2 over f1. This is also same as f1 over q. So this has to be 2, because all these fields are distinct. F1, F2, F3, these are distinct. So this has to be 2, this has to be 2, this has to be 2. Only in that way this degree of the bigger extension can be 8. So there is no other way. So once these degrees are 2, we can see that all degree 2 extensions are always Galois, because we are in characteristic 2. So these extensions are automatically Galois extension. So so how to construct a degree 2 extension of Q? So F1 is a degree 2 extension of Q. So we have already seen in the problem series that uh, if we are not in, if we are in characteristic uh, which is not 2, and suppose E is an extension of F, such that degree of E over F is 2, then E is basically square root of some element. E can be obtained by adjoining square root of some element. So this is one kind of structure theorem for degree 2 extensions. So let's uh, do the easiest one. So
Root 2.
yes, let's take root 2. So let's take f1 adjoint q root 2. So clearly then f1 over q is Galois. There is nothing much to observe here. But how to extend it further such that f2 over q is not Galois? Yeah, any idea?
So, what if we extend another root
Uh, can you be more specific?
q adjoined with root 2, root 5 or something?
Uh, if we take q adjoint root 2 comma root 5 as f2, but then we need f2 over q is non-Galois, right? But is it non-Galois?
Yes, yes. No, it's
Right. So we need to be careful. So what I will do is, so now we need to extend F1 to F2, so that uh, F2 over Q is not Galois.
Sir, what if we take another root of 2 instead of square root?
Yeah, so I will do exactly that same. So what I will do is, I will take F2 as the fourth root of 2, real fourth root of 2. Then you can see that F2 over Q is not Galois, because it is not normal. So why it is not normal? Okay, let me write here. So then note that uh, F2 over Q is not Galois. So can you see why it is not Galois? So what is the irreducible polynomial of fourth root 2 over Q?
X to the 4
Or
minus 2 is equal to 0.
yeah, so it is the irreducible polynomials, and what are the other roots of this polynomial?
Minus root 2, minus fourth root of 2.
Yeah, and the other two?
Then it has another two complex roots.
Yes, so the complex roots. So those roots are not in this field, right? So it
Yes, yes.
cannot be a normal extension.
Yes, sir.
So this is the irreducible polynomial of fourth root 2 over Q, whose uh, roots are basically plus minus real fourth root of 2, and so you need a primitive fourth root of unity. So uh, so
Fourth root of 2i.
so fourth root of 2, this one, and okay, let me just write down
I
I.
and minus I. Plus or
Yes,
minus fourth root of
yeah,
2i.
so let me be more specific. It is just plus minus I fourth root of 2. And note that this plus minus I fourth root of 2 does not belongs to this field, because it's a subfield of R. So it cannot be normal, and in particular it cannot be Galois. We have got F2. Now we need to further extend it to get a Galois extension. So how we will do it?
Sir, just one doubt. Is it Galva over? It is not even Galva over F1 also.
Why it is not Galois over F1? So note
No.
that degree of F2 over F1 is 2. So it has to be Galois.
Ah, yes, 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 yes. Every extension of order 2.
But if
Okay,
you
okay.
want to see why, so find the irreducible polynomial over Q root 2. So in that case, you will see that its irreducible polynomial is just this one. So this is the irreducible polynomial of fourth root of 2 over this F1. So its degree is 2.
Yes, sir. Yes.
So it has to be Galois. So we don't need
Yes.
do that much work, because we are in characteristic 0 and the degree is 2. So it has to be normal, and it is separable, so it's Galois. So now in order to construct the bigger one, now F3 over F2 has to be Galois. So what we have to take as F3? So let me write down the tower here. So it is fourth root of 2, it is Q adjoint root 2, and in the base field we have Q. And now here we have to find F3, so that this one is Galois. Not only this, In particular, this one is also Galois. So how to make this one Galois of degree 2? So what will be a Galois extension of this one of degree 2? Yeah, any guesses? So note that. So this extension is not Galois because uh, the conjugates of this element is not in this extension. So to add the conjugates, what more we have to add? So we just have to add a primitive fourth root of unity, right?
Yes, sir.
So we have to add
I,
basically I. Yes.
I,
So let's take this as a fourth root of 2 comma I. So then it will be a degree 2 extension. So it has to be Galois. And this has to be Galois because this is the splitting field of x power 4 minus 2. Okay, then f3 over f2 is clearly Galois because its degree is 2. But why
degrees
f3
to
over
yes.
q is Galois? So this is Galois because f3 is the splitting field of x power 4 minus 2 over q. Okay, so this example is very interesting because this middle one is not Galois. So one can also ask various questions about this extension like what will be the Galois group of this extension or of these intermediate fields. So I will just write down one information. So you may verify that one. So because it is easy to do also. Uh, so so Galois group of this F3 over Q will be isomorphic to D4. So in the upcoming weeks, we will specifically do how to find the Galois groups. So how to find Galois groups of quartics. Quartics means degree 4 polynomials. Also cubics means degree 3 polynomials. So we will do all these things specifically. So using that, you can also do this easily. But in this example, you can do it just manually. You don't need any other tool. So you just try to verify this. And if you are not able to do, you can let me know. Maybe in the next class, I will help you. So this will be a good exercise. Okay. So we have found the example which we are looking for. Maybe we can move on. Yeah. Okay. So let's do a little bit more involving question. So suppose uh, fx belongs to the polynomial ring zx uh, is an irreducible quartic. So is an irreducible quartic. So quartic means degree 4. Okay. And whose splitting field so whose splitting field splitting field over q over the base field q is isomorphic uh, sorry, not not isomorphic, whose splitting field over Q has the Galois group. Galois group isomorphic to S4, or specifically it is exactly S4, let's say. So that means the splitting field of the polynomial, in other terminology we say it is S4. So let theta be a root of this polynomial fx in that splitting field, and let k be the field q adjoint this theta. Then prove that this first one is what about this degree of k over q, and second one is there are no proper intermediate field. Intermediate field of the splitting field over Q. Okay, I should give a name to the splitting field. So let me write down it here. Whose splitting field, let's say E, there are no proper intermediate field of E over Q. So this is 4. Okay, now let me explain the problem. So we have taken a polynomial fx belongs to zx, which is irreducible and degree is 4. And E is the splitting field of f uh, over q, and k is a field adjoining a root, and we have q in the this field. So we have to prove two things: that degree of this thing is 4. I think I have done mistake because k itself is an intermediate field. So k, yeah, so this should be k over here. So k over q has no intermediate field. Okay, so let me write down here. So E is the splitting field of F over Q. K is a field obtained by adjoining a root of F, and Q is the base field. So first thing is this degree is 4, and this extension has no proper intermediate field. So two things we have to prove. So is it clear, the question?
Yes, sir.
Yeah. Okay. So how to do this? So the first part is fairly easier. So can you see why?
Uh, we are taking the fourth root of a sort of, it's a quartic polynomial, so any root
Yes.
of
So
n is a quartic
degree of
polynomial.
k over q is basically degree of q adjoint theta over q. So this is basically degree of the uh, irreducible polynomial of theta over q. But what is the irreducible polynomial of theta over q? So note that theta is a root of fx, and fx is irreducible over zx. So it is not given that it is irreducible over qx, but it will be irreducible over qx. So first let me write down this. So this is degree of f, which is 4. So this is because uh, f is the irreducible polynomial of theta over q. And why this is? This is because f is irreducible over z. It will imply f is irreducible over q, and this is because of Gauss's lemma. Okay, so I hope it is understandable.
Yes, sir. We done it in while proving Z is a U of D.
Yeah, so it's property of UFD. So this thing has been already done. So let's do the second part. So again, let me draw the picture. So here we have K, Q adjoint theta, and here we have Q. So we need to prove that in between K and Q, there cannot be any other field. So how to do this?
Suppose there is another field, then the extension should be 2.
Okay, let L be another field sitting inside K and Q. Then this degree is 2.
Then
This degree is also 2.
yes, then Q or L is 2 and Q is characteristic 0. So it should be an Q adjoint some element.
Yeah, fine.
Then that element has only degree 2.
Yes.
Then it has an irreducible polynomial, which is degree 2.
Okay, so we don't need that much information, but we need to use the fundamental theorem of Galois theory. So let's do this. So we need to show uh, K over Q has no proper intermediate field. So right, so we have to show this. So suppose L be an L be a proper intermediate field of K over Q. Let me draw this tower a little bit bigger. So here we have this and this. So this is 2, this is 2. But okay, but in that case, E is also an extension of L, right? So what will be the degree of E over L? Note that E over Q, this is a Galois extension. So then uh, basically E over L is same as E over K times K over L, right? So this is same as
Yes.
what is E over
Twice.
K. So how to find E over K? So uh, since E over Q is Galois and its Galois group is given as S4, right? So this will imply this is 24.
24.
So E over K has to be 6.
6.
So E over K is 6. So 6 and it is 2. This is 12. It is 4 and it is 6. So E over K. Okay, I think we don't have to do that much work. Uh, okay, we don't need that much thing. Mm, yes, yes, okay. So this since this bigger extension is Galois, so E over L is also Galois and it is Galois extension of degree 12. So now E over L is also Galois. So what will be the Galois group of this one?
A4.
Exactly. So Galois group of E over L has to be A4 because there are no other subgroups of order 12 because A4 is the only subgroup of order 12 in S4. So
Okay,
now
but
I
then
just
A4 doesn't have any subgroup of order
uh,
6.
need this part. Yeah. So this is 2, this is 12.
Yes.
So then uh, so E over L is Galois. So E over K is also Galois, right?
Yes.
But
Yes. Then
order
E
of
over
this
K
is
is
6.
6.
Yeah, but A4 does not have any subgroup of order 6. So that will be the contradiction. So then
Yes.
Galois group of E over K is a subgroup
Subgroup of
order 6. Subgroup of order specifically this cardinality which is 6 of the Galois group of E
E
over
over L.
L which is A4.
Yes.
But this is not possible, which is a contradiction. Thus, there cannot be any intermediate field of K over Q. Thus, K over Q cannot have any proper intermediate field. Okay, so this proves the second statement. So this is So this problem fairly uses the fundamental theorem and some facts or results from the group theory. So this is a good exercise to grasp the contents. Okay, so let's do one more problem from this problem itself. So this will be a true false type question. So there exists a Galois extension. There exists a Galois extension. Let's say K over Q of degree 4 uh, with no proper intermediate field. So this is true or false. So here
It's
Q means
true,
the
sir.
field of rational numbers. Okay. Yeah. Are you
Okay.
saying something? Yeah. Do you have any answers?
Yes, sir, it's true because we already proved that there exists a Galois extension.
No. Uh, Actually, we
In
have
the
not
above
proved
example,
that
Q
that
extended
one
with
is
P.
Galois extension, right? That we have not proved.
Oh,
So we
yes.
have only told that E over Q is Galois. That does not mean K over Q is
Oh,
Galois.
okay. Okay.
We need to be careful. So in case of Galois extension, this actually cannot be true because of the fundamental theorem. So that's why the previous example. So this example was not Galois.
Oh, yes, sir, yes.
Yeah. So in this K over Q is not Galois. So this is false. Because the intermediate fields are in one correspondence with the subgroups, and a group of order 4 is always have a subgroup of order 2. So false. Uh, since a group of order 4 always have a subgroup of order 2. So then just use the fundamental theorem. Now use the fundamental theorem of Galois theory. Okay, so this is a good observation. Okay, let's do one more. I have one more. Yeah, meanwhile, if you have any other doubts or query, you can ask.
Okay, sir.
Yeah. Okay, so let fx be a polynomial in the ring qx uh, of degree 3, and suppose k be the splitting field, k be the splitting field of f over the field q, field of rational numbers. So suppose okay, too much suppose, and let's say G be the Galois group of this K over Q. So basically G is the Galois group of this polynomial F over Q. That is the terminology we use. It's standard terminology. And this thing is isomorphic to Z mod 3Z. So we are taking a polynomial of degree 3 and we are taking the splitting field and saying that the Galois group is isomorphic to Z mod 3Z. So then show that all roots of f are real. So all roots of f are real numbers. Okay, so k. Okay, let me write down. Let me draw the tower. So here we have k, which is basically the splitting field of f over q, and we have the base field q, and this degree is 3. And the Galois group is Z mod 3Z. Then we have to show that the roots of f has to be all real numbers. It cannot have a complex roots. Yeah, so any idea how to do this?
If we show that if there is an intermediate field L, it is either isomorphic to K or isomorphic to Q,
Yeah,
then is it true that this statement is equivalent?
no, how you are connecting these two?
Suppose there is a field, suppose there is a root which is not a real root,
Okay,
then
then
it should contain I also.
contain I means it is a complex number. It is some a plus ib, where b is non-zero.
Some okay, some primitive root of one. That should
So first thing uh, can be observed is degree of f is 3, right? So it has at least one real root. So since degree of f is 3 and fx is in qx, so f must have a real root. Say alpha. So because complex roots of real polynomials always occur in pairs, right? Since the degree is odd, so it has to be a real root. So let's take it is alpha. So now what can you say about q adjoint alpha?
it should be either isomorphic to Q or to it's either Q
Yeah,
equal to Q or it's either equal to K.
yeah, fine. Q adjoint alpha is exactly equals to q or it is k. Why? Because this degree is a prime number. But so should I write it as irreducible or I think yeah, we need to assume that f is irreducible. Mm, yeah. Uh, x be irreducible of degree 3. Okay. So now if we assume that it is irreducible, then it cannot be Q, right?
Yes, sir. Then it should be equal to K.
Since F is irreducible over Q, so alpha cannot belongs to Q. So it will imply Q adjoint alpha is exactly equals to K. So now, so what this field is actually, how this field looks like. So this is of degree 3, right? So this is basically some A
Yes,
B alpha plus C alpha square such that A, B, C are rational numbers. Now, now K is the splitting field of F over Q. So that means K contains all the roots of F over Q. So this means all roots of F over Q belongs to this field.
yes. And it's a subfield of R.
R, yes. And K equals to Q alpha. This is subset of R. So clearly every root of F is a real number. Okay, this was fairly easier. But what will happen if we assume that F is not irreducible? Uh, so we are not using the fact that its Galois group is 3, right? No, we are using because the degree is 3. Degree has to be a prime number. So if F is not irreducible, then I think its Galois group cannot be Z3. So it is of this form. Uh, so right, if F is irreducible, not irreducible, then it must have a linear factor. So are you getting what I'm trying to do?
Yes, sir. If it's not irreducible, it has at least one root
Yeah,
in Q.
yeah, it has at least one rational root, and the other roots might be complex numbers. But in that case, the Galois group cannot be Z3.
Yes, sir.
Yeah, so basically its splitting field will be the splitting field of that degree 2 factor, and that has to divide 2 factorial. So it cannot be Z1 3Z. So we have to assume that the polynomial is irreducible. Okay, so I think I have covered the things which I wanted to do. Yeah. Mm, yeah. Okay, then if you have no other doubts or queries, maybe we can stop today.
Okay, sir. I'm just catching up. In the lectures, I just reached only in the third week. Next week, I will catch up till fifth.
Okay, yeah. I feel the fourth week is important because in this week the characterizations of Galois extensions are there that I have already listed, and also we have done the fundamental theorem that is important, and some consequences also we have done, and most importantly we have done some examples also. So those things are there. So mostly the characterizations and the fundamental theorem, these are the important things. And some facts are also there. So yeah, but it will not be difficult, and this thing is okay. So mainly the fundamental theorem mostly translates the field theoretic problem to group theoretic problem, so that and interchangeably we can do this, a group theory problem to field theory problem, so that it is important. And while we'll do the insolvability of quintic, we'll use this. So we'll do that part in two ways, by introducing Kumar extensions and also the by the solvable groups. So which is the contribution of Galois. So using solvable groups, we will do the insolvability of quintics, and for that we need the fundamental theorem. I think maybe you can wait for that those things, because those things are there in the later part of this course. Maybe I can tell more about those things in the upcoming live sessions.
Okay, sir. Sir, every week the live session is on Wednesday or
No, every week it is on the Tuesday in the same time, 6 to 8 or 7:30. I think
same Tuesday.
those who have registered will get the email and the SMS also, I think.
Okay, sir.
Yeah. Okay, then maybe we can stop here.
Okay, sir. Thank you very much.
Yeah, okay.